Thank you. I will begin with a word of prayer. Here we go. Dearly Father, we thank you for this day. I thank you for the students, and I just pray that you bless this lecture. Help us to all see it. Amen. All right, here goes. So today we're talking about momentum. So let me just get right into it. You had some papers in there I was going to get back to, but I can't find them now. Oh well. Must have left them back in the math department. I don't know if those papers matter to you or not, but sorry. Something about not having lighting in the classroom is distracting to the teaching for some reason. All right, so here we go. I will eventually... that is really not working for me. I had to turn this thing off. It's blinding me. Well, hopefully the camera picks up something. We'll find out later. To those of you who are not here, I'm sorry, but, you know, this is the cards we were dealt today. So, what is the next part of this course about? It's about momentum. And in particular, linear momentum is what we're currently talking about. A little bit later, about a week from now or so, we'll be talking about rotational or angular momentum. But linear momentum, of course, is associated with straight line motion. And so the basic idea is that if mass m has velocity v, all right, then the momentum of the object is what? P equals to mv. So momentum is mass times the velocity. You might notice that momentum is a what? Momentum's a vector, right? Now, a lot of times we work problems which are one-dimensional, in which case we can just use a number to represent momentum, and then the sign of it, plus or minus, will indicate left or right. But generally, two-dimensional or three-dimensional problems, we got to think about momentum as a vector. Let's see what momentum has to do with Newton's equations. What's Newton's second law say? It says that the net force, right, is equal to the mass times the acceleration vector, right? What's the acceleration vector equal to? It is equal to the mass times the change in the velocity vector divided by the change in time, right? Change in velocity over change in time is the acceleration. Now, if the mass is constant, I can rewrite this as the change in the mass times the velocity divided by the change in time. All right? So, but what's mass times velocity? Anybody happen to have a 100-watt bulb on them? No? Nobody? Thing is, I got some better lights in my office, but I don't want to walk all the way out. Fine. All right, I'm gonna stop. Can you guys see this at least? Everybody's here? Okay. So what is m times v? Well, that's the momentum, right? So what we have is the change in momentum divided by the change in time. So another way of looking at Newton's second law is to say that the net force is equal to the change in momentum over the change in time, or the average rate of change of the momentum. If we had calculus, right? If we had calculus, this thing, and some of you have had calculus, so let me just write this for the sake of those who have had it. The deltas become d's, the mass becomes constant, so we can pull it inside, right? So this is, if you want to think about what I just wrote instantaneously, that's what it looks like with calculus. Some of you have had calculus, so it's worth me writing that. If you haven't, don't worry about it. It's not a big deal. So what does this say? The net force is equal to the change in momentum over change in time. Now, by the way, the change in momentum is also called the impulse. So the impulse, or the change in momentum, is also a vector quantity. All right. All right, so let's move on here a bit. What would happen if we have more than one mass? What if we have two masses? Then the momentum would be m1 v1 plus m2 v2. So the net momentum is the sum of the momentum for the first mass plus the momentum for the second mass. Momentum is additive, like the net momentum is the vector sum of all the momentums of the particles that comprise the system that we're thinking about. In this case, a system with two masses. And by the way, you can write down, it's in fact true that the net force, it's still true for 2, that the net force is equal to the change in momentum over the change in time. All right? What's that? What happens if the net force on the two masses is 0? What if the net force on both of these masses is 0? What happens then? Then we have that the change in momentum over the change in time is equal to what? Right. What does that say about? There's no acceleration. That's also true. The net acceleration of something that I haven't talked about yet is 0. It's true. But yeah, the change in momentum over the change in time is 0. But what is this? I mean, so change in time being non-zero, we can just think of this as being the change in momentum being 0. So what's that say? That says that the momentum of the system stays the same before and after a process where there's no net force. All right? So what I'm saying is that if the net force on a couple of masses is 0, then their momentum is conserved. So what this says is that the final momentum is equal to the initial momentum. All right? Now, what's the final and initial momentum here for two masses? Right? What we have is the momentum of the first mass, the final momentum for the first mass. Blech, I can't say words today. The final momentum for the second mass is equal to the initial momentum for the first mass plus the initial momentum for the second mass. Momentum is conserved. When is this true? When is momentum conserved for a system? The answer is when the net force on the system is 0. Right? Now, if the net force on the system is not 0, then momentum doesn't have to be conserved. All right? Let's think about projectile motion. If we think about projectile motion, think about, you could think about projectile motion where, if you wanted to think about two masses, you could think about if we thought about a cannon, right? And I don't know, we've got like a giant arrow, and let's say that on the arrow we put a cat, and then the cannon fires, boom. And then like up here, later, there's the cat, right? And then the cat falls. The cat like drops off the arrow and starts falling down, right? Does he die? I mean, we could be optimistic, I guess. But cat falling. Ah! I mean, it's a cat, so it's going to fall on its legs. But to complete the story, there's lava. Lava. There we go. Just to make sure it's an optimistic story. But my silly question for you is momentum conserved? If I look right after the moment it's fired, right? The cat's on the arrow, and then the cat rides the arrow up to the top of the zenith of the flight, like that, and then it drops off. All right. Would momentum be conserved in this process? That's right. There's gravity. And gravity is an external force. That's a net force on the system, which is not zero, which means momentum is not conserved. Exactly. So the momentum would not be conserved in this problem because there's a net force of gravity. When is momentum conserved? Momentum is conserved either when the time scale is so short that there's not time for forces to really change the momentum. That's one case. Or the other case is just you're in a situation where there's just no force, like maybe a couple of ice skaters on an essentially frictionless like pond or something. They run into each other, I mean, there's the gravitational and normal force, but those are acting perpendicular to the motion. They don't really involve themselves in the collision. So you could have like ice skaters, colliding into each other. That would be a place where you could have momentum conservation there. But the principal thing, actually, what I was just talking about is collisions. In a collision, you have two things like smash into each other and then bounce off, right? That's happening so fast that there's not really time for the forces involved, external forces involved, to change the momentum, right? Like, what are the external forces for two cars crashing into each other? If we just think about the two cars as the two masses. Well, the external forces would be things like gravity, right? And more notably, the friction force, right? Or, well, there could be like a force from hitting a guardrail. That's not what I'm talking about. That's definitely not negligible. But if you're just thinking about the cars hitting each other and then starting to skid, the friction force is pretty small. It doesn't really have enough time to change the giant momentum of the cars. So to a good approximation, you could ignore the friction force changing the momentum over the process of the collision. So like right before the cars hit to right after they skid off, either together or bouncing off apart, that's a place where we could use conservation of momentum to study what happens before and after, because there's not time for that net force to change the momentum. So that's the big idea, is we can use conservation of momentum to study collisions. All right, so we'll get back to that, but for now I think I should just do some basic homework problems from this section to make sure we understand what momentum is, right? So which problems have I assigned? I'm just going to work some of them, if I can find them. I took a picture. That seems like cheating. Let's see here. Page 192, number 45, number 50, number 67. Let's see, which one am I supposed to work on? Oh, yeah. What on earth? That seems like cheating, though. Okay, all right. I took this photo. I'm trying to use it. Fine. You make a good point. Thank you. I'm stuck in my ways. What can I tell you? Actually, 164 to 169, we've talked. You already have experienced that on your quiz to a certain degree. I'm going to work like something from 192, maybe 1, 3, 5, 7, 11, something like that. Let's start out with something really easy. Number 1. 192. I do have a 500-watt shop light that I'll be bringing in here next class if this isn't fixed. It'll be bright. Just don't touch it, it'll burn you. All right, number one. Number one of page 192. Number one says the following: what is the magnitude of the momentum of a 28-gram Sparrow, European? Let's see here. Flying with a speed of 8.4 meters per second. This one I'm kind of embarrassed to even be writing out on the board, but you know, you're like, no, this is a good test question. Yeah, you guys. So 28 grams, let's rewrite that as 0.028 kilograms, yeah? And 8.4 meters per second. So what's that work out to? So the first bunch of homework problems are pretty much just going to be about understanding what is momentum defined to be. Once we get the hang of that, then we'll start solving collision problems. That's how it's going to go in here, okay? 0.028.
So we're just finding the momentum of this?
Yep, this is just the momentum, and this is the magnitude of the momentum, because we haven't been given any kind of direction or anything, so this is all we can do. This is the magnitude of the momentum, 0.2352. I think. And what would that be? We got ourselves kilograms, meters per second. That is the units of momentum. I mean, you know, so the units of power are watts. The units of energy are joules. The units of force, newtons, right? But momentum, we got no name for the units. We just write kilogram meters per second. There's no, as far as I know, there's no like special name for momentum's units. So it's kind of funny, right? Maybe we should call them like mementos or something. I don't know. Call them drakes. Very nice. Let's not get crazy. Let's see here. Let's see here. Okay, this is number 3 is a good problem actually. Let's work number 3. This is pretty typical test question, number 3. We've got a 7,150 kilogram railroad car, travels alone on a level frictionless track with a speed of 15 meters per second. So here's the initial thing. Got your railroad car, I don't know, whatever, it's a railroad car. And it's traveling, where was I? 15 meters per second. The mass of the railroad car is what? I'm going to call that M1. The mass of the railroad car, M1, is 7,150 kilograms. And it's traveling on a frictionless track at a constant speed, 50 meters per second. It says then a 3,350 kilogram load initially at rest is dropped onto the car. What will the car's new speed be? All right, so here's before. What is it? I said 3,350. Let's call that M2. So afterwards, what do we got? We have the railroad car, which I'm drawing badly, and the load on top of the car, like so. What after the load is dropped onto the car afterwards, we have final velocity VF. We don't know what that is, right? Now, if the load is dropped onto the car, do they both have the same speed after the load is dropped onto the car? They're stuck together, so whatever that final velocity is, both mass 1 and mass 2 both share that mass. How about this? No, it's a frictionless track, right? Which means they're giving us license to understand that the net force on the system is 0, right? This is a situation where momentum is conserved. So, what's the initial momentum? We've got M1 times v, well, let me just write the numbers then if you don't mind. 7,150 kilograms times 15 meters per second, that's the initial momentum, right? What's the final momentum? So final momentum, both the load and the car have a velocity vf. They both share momentum. And so the final momentum would be, m1 vf plus m2 vf, right? Which we could do algebra. That's m1 plus m2 times vf, which is what? What's m1 plus m2? 10,500. And then as usual in here, we do algebra, and we find that Vf is equal to, okay, so 15 meters per second times 7,150 kilograms divided by 10,500 kilograms. The kilograms cancel, right? Just leave us meters per second, which is good, because we're trying to find a velocity, right? That gives us comfort. So what we got here? I get 10.21 meters per second. Does that make sense? Does it make sense that the speed is smaller than it was at the start? Right. Right. What do you guys think about the kinetic energy in this situation? Is kinetic energy conserved here? Yeah, it's not actually. If you were to calculate the kinetic energy of the initial car and contrast it with the kinetic energy of the combined system going at 10.21 meters per second, what you'd find out is that there was kinetic energy lost. Where did that energy go? Yeah, friction, like just the process of that mass glomming onto the car, it takes energy for that to happen, yeah.
I understand how we got the meters per second, but can you go back to how you decided that it would be Vf equals the speed and then the weight of m1 and m2?
So the equality right here, I'm saying that the initial momentum is equal to the final momentum. What's the final momentum? There's two things to think about. There's the momentum of the car, There's, well, let me not invent new labels. The momentum of the railroad car itself is m1 vf, but the momentum of the load once it starts moving with the car is m2 vf. They share the same velocity, so yeah. Right. Well, again, momentum's conserved, so we can set the initial momentum equal to the final momentum. So. All right, let's work another one. What do you guys say? Let me skip ahead here a bit. Number 11 looks interesting. Let's see if we can figure that one out. So here we have a 22 kilogram, listen to me, that would be a big bullet. 22-gram bullet. And what happens to it? It's traveling 240 meters per second. Let's say that's V naught. It penetrates a 2-kilogram block of wood. All right, 2-kilogram block of wood. And what happens to it? And it goes right through it. Right? So it rips through this wood, it maybe cuts a hole through it like that, and then the bullet comes out the other side, right? The mass of the bullet, I think, is still the same, right? Yep. And when it leaves, the bullet is going a final velocity of 150 meters per second. So it's slowed it down. That makes intuitive sense, right? shoot a bullet through a wall or something, it's going to slow it down a little bit, right? So this is the question. If the block is stationary on a frictionless surface when hit, how fast does it move after the bullet emerges? Let me repeat the question again. If this block is originally at rest, right? And then after, let's see, this is before. So before, you've got the wood sitting here minding its own business, right, with initial at rest. And then after the bullet has shot through the wood, it's going 150 meters per second. And the wood is doing what? Is the wood sitting at rest still? It is not, because if it was, that would violate the conservation of momentum. The original momentum of the system is what? What's P naught? It's 22 grams, which is 0.022 kilograms, times 240 meters per second. That's my initial momentum. What's my final momentum? What's the final momentum here? We got to identify what are all the momentums involved. Now, one of them's easy, right? It's the momentum of the bullet slowed down. What's that? That's 0. We're assuming the bullet doesn't come apart or anything, so it's still got 22 grams, it's 0.022 kilograms, times 150 meters per second. There you go. That's the momentum of the bullet after it emerges from the wood. But what else is there? There's the momentum. Now, see, these can't be equal, right? This is not equal to that, which is going to show you that there is also, let's say, VW for wood, a velocity for the wood, right? And I don't know what that is. That's what we're trying to figure out, right? So plus 2 kilograms times the velocity of the wood that we don't know. That's momentum conservation. Does that make sense? I hope so. And so we can solve for VW, and that's the answer. So VW is equal to 0.022 kilograms times 240 meters per second minus 0.022 kilograms times 150 meters per second, all divided by 2 kilograms. Whatever that is, that's the speed of the block. What is it then? I get 0.99 meters per second. So what do you guys think about that? Does that make sense? Do you have any questions about this problem? Let's look at number 13. Number 13 investigates a slightly different direction of this discussion, all right? So number 13 is a good one to look at. This was what? This was number 11, right? Okay. And again, this is page 192. Let's look at number 13. Number 13 says the following. It says, air in a 120 kilometer per hour wind strikes head-on the face of a building 45 meters wide by 75 meters high and is brought to rest. Okay. So here we've got building. What was the building? What did we're told what it was. 45 meters wide. And how tall was the building? 75 meters high. Yes. Something they're putting in the food down there at Mountain View is making people giggle. That's what it is. There we go. All right, where are we? So 45 by 75, and the air is brought to rest, all right? If the air has a mass of 1.3 kilograms per cubic meter, determine the average force of the wind on the building. So we've got air. And we're told that the velocity of the air, the speed of the air, is 120 kilometers per hour. All right. And that the mass is, what is the mass here? Given by 1.3 kilograms per cubic meter. We're supposed to find the average force of wind on the building. All right, let's see if we can think about how to do this. So the net force, right? Well, the force of the air is going to be equal to the impulse of the air, per unit time, right? So how can we figure out, and so that should be the, and so to, I guess we could use any increment of time we like because the time is constant here, right? What would be a convenient time to use given the units that we're given here? Seconds? Yeah, I think if we use delta t is equal to an hour, then that's convenient for the purposes of our units here. But I would usually think about it being a second, honestly. Yeah, my first inclination is to use a second, but.
Wouldn't we have to convert it once we get it so that we can have seconds?
Well, the first thing I want to think about is, I don't know. So the question is, how much air is hitting the wall in an hour? Let's stick with an hour for a second. So what's the mass of air hits what's the mass of air hits wall in 1 hour? How do we figure that out? What would that be? I believe it would be 120 kilometers per hour. Well, we can just say 120 kilometers because we're multiplying by the hour. So 120 kilometers. And what's the area? 75 meters times 45 meters. That's the volume of air that hits the building in an hour. Does that make sense? That's the volume of air which hits the building in an hour. If I take 1 hour, there's that much volume of air hitting the building, right? Does that make sense? So I'm doing meters times meters times meters. This is a volume. It's got a units of meter cubed, right? Then how do I get the mass? I multiply by the density. What's the density? This is density here, right? Density is kilograms per cubic meter. So I multiply this by 1.3 kilograms per cubic meter. You notice what happens. That's the density. The meters cubes cancel, and that gives us the mass of air that hits the wall in an hour. Admittedly, an hour is kind of a silly time to use, but it's convenient for the calculation. So 120 times 75, 45 times 1.3 times 1,000. Yes, you do. I mean, this is 526500000. Let me put it back into, somewhere in my calculator there is a, oh, there's a button here for putting it into scientific notation. Yeah, I've forgotten which button that is. Oh, there it is. 526.5 times 10 to the 6th. Times 10 to the 6th kilograms. What's that? I did. I multiplied by 1,000. So that's a 10 to the, that's like 5.265 times 10 to the 8th. So 10 to the, I think it's, what was that? I think it's okay. New noise. Always a new noise in here. There's no telling what's going to happen next in this classroom. This is like the most exciting classroom at the most exciting university, right? So there you go. Are we still the most exciting university? I lose track. What's our current tagline? We were advertising to be the most exciting a few years ago. That's probably why some of you came here, right? To be at the most exciting university, am I right? Yeah, right. It's Snowflakes, that's why you're here, am I right? Oh, yeah. That thing scares me, I don't know. When my kids go down on those tubes, you know, no, I don't like it. Scary for me. Okay, so that's the mass that crashes in to the wall and just drops, is the problem tells us. And that's, what's the velocity of it? So this is what? This is change in mass times velocity divided by change in time. So I'm saying that this is exactly 526.5 times 10 to the 6th kilograms. What's my speed? 120. Man, what? 120 kilometers per hour. Oh, okay, I got it. And then divided by 1 hour. So these hours cancel. Well, no, they don't. That gives me an hour squared. Oh, that's obnoxious. Oh. All right, I can't avoid the hour calculation. We're stuck with it. So, fine. 526.5 times 10 to the 6th kilograms rather, times 120 times 10 to the 3rd meters, divided by 3,600 seconds, quantity squared. That should give me the force in newtons. Here goes nothing. Times 120 times 1,000 divided by, I get 4,875,000 newtons. Or let me write it in a more civilized way. I get 4.875 times 10 to the 6th newtons. So that is, what was the question? Goodness gracious. The book says that's right. Oh, well then, at least we're both wrong then. Or right. Yeah, so I guess that's there you go. All right. I like the idea of this problem, but I don't like the numbers in it, and I don't like the way it's worded, honestly. All right. You're like, why'd you pick it out? Hey. Let's not think about those kind of questions. All right. Number 15. 0.145 kilogram baseball is pitched at 31 meters per second on a horizontal line drive straight back to the pitcher at 46 meters per second. If the contact, this is better. This is a better average force question. This is clear. It doesn't involve some sort of weirdo density calculation like that one. We can still say weirdo, right? It's not like some kind of like word police about that word yet, right? I think it's only a matter of time, though. I don't know. Where was I? Yeah, this one's not bad. Let's get to it. Number 15. So we have a baseball. How big is the 0.145 kilogram baseball? All right. And it's initially 31 meters per second. All right. Then what happens? Horizontal line drive straight back at the, so there's Mr. Top Hat over here. And he's got a bat, which he's holding in some sort of rather awkward, unphysical way. And he hits the ball back at the pitcher. And when he hits it back, the ball has a speed of 46 meters per second. All right? The question then is, if the contact time between the bat and the ball is 5 milliseconds, calculate the force between the ball and the bat. So, you know, what happens is there's this moment of time, right, where the baseball bat drawn badly impacts the ball, right? And the ball smushes, and then the ball rebounds. And that smushing and rebounding process, we're saying, takes a delta t, like the smushing and smooshing / rebound of ball over 5 milliseconds, also known as 0.005 seconds. All right? So the average force is the change in momentum over the change in time. We don't need vectors here because there's no directionality to the problem, right? Where do you use vectors? You use vectors when we got like a 2- or 3-dimensional problem, right? That's not this. Okay, so what's the change in momentum? So we have mvf minus mvi divided by delta t. And we can factor the m out, right? So m is 0.145 kilograms times what? 46. Well, that's the thing is we got to you got to make a choice. Which direction do you want to be positive? Is right going to be positive? Okay, if right's positive, if right is positive, then VI is equal to 31 meters per second, and VF is equal to minus 46.0 meters per second. That's how we have to keep track of direction in one dimension with signs, plus and minus. And that's important because over here we have minus 46.0 meters per second minus 31 meters per second divided by, what was my, oh yeah, 0.00005 seconds. Now, in order to not take off more points than I want to, I usually ask for the magnitude of the force, which frees me of making sure you've chose the right sign for your force, right? This is going to be a negative force. Why is that? Right, the bat is applying a force to the left, right? In order to return the ball's motion from the rightward direction to the leftward back direction, we require a leftward force, which is negative because you guys said right was positive. It's all your fault. All your fault. Let's see here, divided by 0.005 times 0.145. Yes, this would be in newtons. And so what I got is minus 2,233, that's a fun number, newtons. Now, there might not be a minus sign because I have probably just not been careful to read the wording of the problem. Let me read it again. Calculate the force between the ball and the bat. I mean, you know, the physics book is not always super careful about what they're asking for. So, I mean, technically speaking, the answer in the back of the book might be 2233. Towards the pitcher. Oh, okay, well, that's good. And that's what our answer means, right? Minus 2233 is towards the pitcher, because the pitcher is over here, not pictured, because I only know how to draw one kind of stick figure. Okay, let's see here. Let's move on to another problem. Let's see here. Actually, number 18 is a good problem because it contrasts this one nicely. It's kind of the same problem. Same page. Page 192. Number 18. Now here, we have like a wall, and we've got a ball. It comes in, do-do-do-do, and then do-do-do, like so, all right? And there's 45 degrees here, and there's 45 degrees here. So the ball hits the wall, tennis ball hits the ball. So the mass of the tennis ball is given to be 0.06 kilograms, all right? And the speed, originally 28 meters per second, and it rebounds with the same speed. The same speed rebounds at angle 45 degree. The question is, what's the impulse, magnitude, and direction given to the ball? And it says as a vector, right? We want the magnitude and direction. By the way, this is long overdue in here, like long overdue. Two-dimensional vector can be written as a magnitude and direction, right? Right? You know this? So if this is the vector, v, we can rewrite it. Let me not use v because we think of v as being velocity. So let's say a. We can take a vector a and write it as a hat. All right? And in this a hat, if you go direction, if this is theta, a hat is given by cosine theta, sine theta if you like. So it's a unit vector which points in the direction in which the vector is pointing, and then the magnitude is just a. So like here, if a is equal to, say, a1, a2, then the magnitude of a is the square root of a1 squared plus a2 squared, right? So this is just some background. Any two-dimensional vector we can write as a magnitude times the direction, right? And for 2 dimensions, the direction is uniquely fixed by the standard angle in the sense of polar coordinates, right? You rotate counterclockwise off the positive x-axis, that's the standard angle. That uniquely fixes a direction. If you give me a standard angle, I know which direction you're talking about. Now, in 3 dimensions, standard angle stops being so useful, right? But anyway. So what's the impulse here? So we need to think about momentum as a vector in this problem, right? What's the initial momentum? It's the mass times the initial velocity, yeah? What's the final momentum? It's the mass times the final velocity. Can we write down the velocity vectors before and after? What is VI? It's equal to the speed times the unit vector in the direction, right? if you put a hat on something, it gives it unit direction. So like VF, I can write as the speed VF times VF hat. If you put a hat on a vector, that makes it a unit vector, right? So like, you know, depending on your system of measurement, it's a hat you don't want to wear, right? I mean, if you put the hat on, all of a sudden you become a meter tall. You know, I mean, some of you, I don't know, maybe some of you dream of only being a meter tall. Maybe someday you will be. You know, as you age, you shrink. It's possible. Or maybe if a unit was more than a meter, like if you're working in inks, if you're working in you know, like astronomical units, if you could be a unit vector, well then you'd be really long. But it's a tough crowd today. See here. Okay, so what is VI hat? It's like this, right? This is VI hat. What is that vector? I think it's cosine of 45 degrees, sine of 45 degrees. Do you guys agree? That's the initial direction. It's up both x and y 45 degrees. So that's the unit vector like that. Over here, what's the standard angle for the final one? Can you guys tell me what the standard angle is for this right here? We go like that, right? Theta equals to 90 degrees plus 45 degrees. So over here, I could do cosine of 135, sine of 135. If I wanted to be lazy. Of course, if I wanted to think for a second, could you write those in terms of sine and cosine of 45 degrees? I think you could. Right? This VF hat, we could also rewrite as minus cosine of 45 degrees. Is this vector still going up? It's still going up, right? I mean, both of the initial and the final velocity vectors have the same, what? Same vertical component. So if you understood that conceptually, you could just focus your attention on the change in the horizontal, right? Because that's where the whole impulse is coming from. The impulse is going to be purely horizontal when we work out the math here. So I'm going to keep working out. All right, so I have done the legwork to show you that Pi is equal to the mass times the initial mass times, let's say, let me call this 28 because I'm going to get sick of writing it. We just call that V naught. So mV naught times VI hat. Oh, goodness gracious, guys. I'll just put numbers in. I know it's driving you nuts. So we've got 0.06 kilograms times 28 meters per second times, what's the initial unit vector? You know, cosine 45, sine 45. The final momentum is the same 0.06 kilograms, 28 meters per second, because it's got the same final speed, right? But this time, minus cosine 45, sine 45. So, let's see here. Maybe you guys can actually tell me the specific numerical values. What's PF equal to? Let me work it out. Sorry. So the coefficient in the front is 1.68. I get 1.188 of course, kilogram meters per second. And then what's the other component? Well, the same, right? It's 1.188 kilogram meters per second. What's the initial momentum? Oh, I'm sorry. That is the initial, isn't it? Sorry about that. Initial. What's the final momentum? Same numbers, but different sign, right? Minus 1.188 kilogram meters per second and 1.188 kilogram meters per second. What happens when we subtract these? What's PF minus PI then? That's the change in momentum. That's the impulse, right? And what is it, though? When we subtract these vectors, the vertical components cancel. And what are we left with? We're left with minus 1.188 kilogram meters per second times 2, comma 0, which is minus 2.376 kilogram meters per second, comma 0. And how could we put that into words? What's the impulse? The impulse is 2.376 kilogram meters per second, directed which direction? To the left, right? I mean, correct. Do you check the answer in the back of the book? I don't know, it's like, it feels amazing when you get the answer in the back of the book, right? We'll never know. But no, this is the right way to work this problem. I'm just kidding. I actually do understand physics. I may or may not understand the mathematics which students are actually able of doing in physics, but the physics I understand. Let's see here. So, let's see here. Where was I? Number 18. Which math? So what we're looking at here, this bit right here, that is the initial velocity. So I'm writing the initial velocity as the speed times the direction. Likewise here, this is the speed, and this is the direction of the final velocity. How did I multiply it out? Oh, I just multiply, sure. If we have a constant times v1, v2, the rule for multiplying the vector is we do c times v1, c times v2, just like that. So, yeah, okay. That question I can answer. So, specifically, what we're looking at is 0.06 kilograms times 28 meters per second times the cosine of 45, and then 0.06 kilograms times 28 meters per second times the sine of 45. I mean, that's what went into the, that was the nuts and bolts of that problem. Yeah. All right, let me look ahead here for a minute. Problem 21, 23, what do those look like? I think 21 is a good one for you guys to work out on your own. Make sure you understand the idea. I'm going to leave that one for you guys to work on. I think you're going to get it. It's a pretty standard problem. I don't think that one's going to be too bad for you. 23 involves math, which I haven't explained yet, so it's probably good for me to talk about 23 for a minute. So 23 gives us this graph, all right, of